Okay, let's hope nobody else calls here. All right, from Tulsa, I want to go 83 miles west and 63 miles south. Now I'll go back west, like so. No, not like so. Like so. And I shouldn't cross through here because 83 is less than 107. Now you don't have to be exact, but let's say I put it right there. And let's go 63 miles south, so we can continue going south of Tulsa. So let's say about there. So if you wanted to draw another resultant vector, for instance, I could put another black route there. Again, these aren't exact ways that they drove or anything, but these would be exact distances from there to there is here, from there to there is here. Draw a diagram to show their trip, so that's kind of what I did. Then tell where Norman is in relation to Enid. So I don't think they want the trigonometric way as how we did with resultant vectors. But if I wanted to give a jump start on that, I would maybe draw a bigger black line resultant vector and saying that's actually how far away I am from Enid. But I think they want the x and y, or the directions this way. How far did I go east? How far did I go south to finally get there? So what we want to actually find out, and I'll use one last color here, is I want to find out how far I went that way and how far I went that way in the end. And if you really wanted to find out this, you could use Pythagorean theorem and tangent to solve for the angle, or inverse tangent, rather. Okay, so if I went 107 miles east this way, and eventually I went back, let me label these, eventually I went back 83 miles west, and let me get 63 here. So if I went 107 miles east, and let's call that the positive direction, or at least the eastern direction, and then I went back west 83 miles, that means I'm kind of subtracting my eastern miles. So I subtract those two, and I get 24? I get 24 miles east. And let's call south positive in the sense that I want to say I went 18 miles south, and then I went 63 miles south. As long as you indicate direction, anything can be positive. So negative north, for instance, is positive south. That is 81 miles south. So here's my diagram. Here is my final point, Norman. And Norman is 24 miles east and 81 miles south of Enid. So that's kind of like your final answer there. That would be the last thing you would put. Number 39, and this one I will do with matrices, and it will kind of be long and expansive, but for your benefit, so you do understand maybe more how matrices work, or perhaps more to confuse you. I'm really not sure how it'll end up, but I do want you to see matrices again and really start to get a gist of it, especially for Algebra 2, once you start doing it. Triangle MUG has coordinates M at 2, -4, U at 6, 6, and G at 7, 2. So the first thing I'm going to do is design a matrix with these 3 points. So this is I think it's called a 2 by 3 matrix. I think you do rows first. So I'll do two points here, 2, -4 for my x's and y's, 6, 6, and 7, 2. A translation maps point M to M prime at 3, -6. So basically, if my point M started at 2, -4, and my M prime is at -3, 6, what does my translation look like? That's kind of what they're hinting at you solving for first. And then based on the translation you find the coordinates of U prime and G prime under this translation. So whatever, and let's call that translation for now A, B. We'll figure out what it is. And you can probably figure out without looking at all this matrix stuff that I'm doing. You can probably eyeball it or use the own math that you do know how to do. But for the sake of matrices, let's look at it this way. That way you can really see all the math that goes on. So if I take this matrix here and I add what I call a translation matrix, where I have to add A's to all of my X's, and remember, it needs to have the same amount of columns here. So A's to all of my X's, like 2 plus A, 6 plus A, 7 plus A, and B's to all of my Y's. Then eventually I will land on the triangle, which is in isometry, but I'll land on this triangle with this M prime, U prime, and G prime. Now they only gave us what m prime was, which is negative 3, 6. So I'll go ahead and call this x2, y2, coordinate points that we have to solve for, and x3, y3. So in order to solve for these a's and b's first, let's rearrange this this equation a little bit. So let's take MUG. Let's subtract this matrix over here. So subtract it on both sides of the equation, and eventually we will get A, B, A, B, A, B. So this equals this subtraction. M prime, U prime, G prime. And I'll fill that in 1 second. Minus MUG. It should be a U. And I want to make this a little lighter again. So M prime is negative 3 and 6. And we got X2, Y2, and X3, Y3. Now keep in mind, this is a subtraction now. I subtracted it from both sides. So whenever you do these things here, you're going to have to make sure that you subtract all of these values. Now, all three of these a's and all three of these b's will be the same value. In other words, one a won't be different from the next, but these coordinate points will be different. So if I do the subtraction now, I'll say that all equals, let's do negative 3 minus 2 for this entry on the top left. The middle part will have x2 minus 6, and the top right will have x3 minus 7. And on the bottom, we'll have 6 minus negative 4, y2 minus 6, and y3 minus 2. And in the end, that equals... actually, let me just take that and extend this a little bit more and rewrite these again. So I have those my translation matrix. The translation matrix here, A, B, 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 that equals negative 3 minus 2 is negative 5. 6 minus negative 4 is 10, which is 6 plus 4. And I still have x2 minus 6, y2 minus 6, x3 minus 7, y3 minus 2. So what we've come to figure out, remember all of these entries tie in together. Let me color code these. This A ties into this negative 5. This B ties into this negative 10. Now all of these A's all tie into the same thing. So this A ties into here, this A ties into here, and the B's tie into here and here. So one thing we discovered, although we didn't solve for x2, y2, x3, y3, or these particular entries, we have solved for these. We found out that A equals negative 5. And we also found out that B equals 10. So I could now rewrite this translation matrix into all sets of negative 5s and 10s, as in negative 5, negative 5, negative 5, 10, 10, 10. And I could say that it equals this same thing over here on this side, which I do apologize for me rewriting all these things over and over. This isn't exactly how I'd ask you to do it. I'm just giving you a very broad example of matrices to make sure that maybe you can see everything through nice and clearly. So if I translate everything right here, then this is what everything here will equal on this side. So let's see. So how can I now solve for x2, y2, x3, y3? Well, I can start substituting values in. x2 minus 6 equals negative 5. So I can write an equation for that. I'll say x2 minus 6 equals negative 5. Add 6 to both sides, I get x2 equals 1. So I could just say, oh, cool, awesome, I got 1 for that. And keep doing the same thing for everything else. And I'll plug those in later to not have to change all the settings again. So x3 minus 7 equals negative 5. So x3 equals 2.